Okay, today I'm going to discuss a few problems from the Unit 2 of CYU 4303 Organic Chemistry 1. These are actually review questions which are available at the end of each session of Unit 2. And, doing these review questions is going to be very useful for your final exams or any exam of CYU 4303. Okay, let's look at the first question that is from Unit 2, Session 2, and this is review question number 1. It says, explain why the rate of hydrolysis of tertiary butyl chloride in water is unaffected. Unaffected, that means no effect, by the addition of a small amount of sodium hydroxide, while ethyl chloride is unreactive in water but with addition of sodium hydroxide. So ethyl chloride, they say ethyl chloride is unreactive in water, but with addition of sodium hydroxide, the hydrolysis takes place at N, rate increases with increasing amounts of sodium hydroxide. So here we're talking about the tertiary butyl chloride hydrolysis. So hydrolysis is a type of solvolysis. So we learn about solvolysis. Solvolysis means you break bonds with your solvent. Okay. With your solvent. So solvolysis. Lysis means you break. Solvo means, that's a solvent. But hydrolysis is a special type of solvolysis. Because in hydrolysis, solvent is water. So that is why it's called hydrolysis. Hydrolysis of tertiary butyl chloride. So tertiary butyl chloride is this. So you have tertiary butyl group and chloride. And the other one is ethyl chloride. Okay. So this is a tertiary tertiary alkyl halide. This is primary alkyl halide. Okay, let me see that. Okay. So the question is, this hydrolysis of tertiary butyl chloride, they say adding hydroxide, sodium hydroxide, has no effect, but this happens in water efficiently. But hydrolysis of ethyl chloride, so in water it does not happen, but if you add sodium hydroxide a little bit, the reaction will happen. And also if you increase the amount of sodium hydroxide added, the rate will increase. So here we have to compare the rate, rate of this reaction. Okay. So these are the two chemical species that we are comparing. And so then we, when you've been given, this kind of paragraph, it's better that you draw the structures separately and write down the reactions, as flowcharts, as I have done here. So that'll make it easy for you to analyze the reaction. Okay. As I said, okay, let's look at the answer, like how we approach the answer and how we write the answer. So we know that tertiary butyl chloride, it's a tertiary alkyl halide, and so it is, we know that we learned about these alkyl halides and then nucleophilic substitution reactions under Unit 2. And we know that alkyl halides, they undergo SN1 or SN2 mechanisms. And depending on the structure of the alkyl halide, especially tertiary alkyl halides, they undergo SN1 mechanism. The reason being, when you have tertiary alkyl halide, and it makes tertiary carbocation like this one, and they're more stable, because carbocation, to make it, to make the positive charge stable, you need more alkyl groups attached to that carbon so that they can pump more electron density to diminish the positive charge, or to remove or to decrease the positive charge. That's why the tertiary carbocation is more stable. And in the SN1 mechanism, we know that the first step is to remove the leaving group, which is this halogen, and make the carbocation. So this is the carbocation. And so that step is the rate determining step, or the slowest step. And because in SN1, there's only one chemical species involved. So that is why it's called SN1. SN means nucleophilic substitution and one chemical species. And the carbocation formation is the rate determining step. So therefore, if you write the rate law for this reaction, it will have only the one chemical species of the tertiary butyl group in the rate law. So therefore, the rate depends only on the tertiary alkyl halide. And so therefore, rate law will be rate equals rate constant times the concentration of the tertiary alkyl halide. It could be chlorine or bromine, it doesn't matter. So whatever the alkyl halide you have, so it's a mistake. Then followed by, after this slow step, followed by this will undergo attack by the nucleophile, the water. So because this is hydrolysis and this is happening in water, no side of sodium hydroxide added, nothing. And these steps are faster, so this will attack and have this intermediate where oxygen has a positive charge, which is not stable. This water can act as a base as well. So so it will abstract this proton and breaking this bond onto the oxygen positively charged oxygen, then taking care of that plus charge, and you have this final alcohol. So the hydrolysis of alkyl halides will give you alcohols that you have to know. So the tertiary butyl chloride, with water, you get this alcohol. Hydrolysis of alkyl halides will give you alcohols. So let's analyze the other one as well. Ethyl chloride or ethyl bromide. So this is actually a primary. This is primary alkyl halide. We know that primary alkyl halides, they undergo SN2 mechanism. So nucleophilic substitution with two chemical species. Both substrates will be there. So in that case, you leaving group, the removal of the leaving group or the leaving of the leaving group and attack by the nucleophile will be happening at the same time. So we call it concerted mechanism. So it's a concerted process. So therefore the rate depends on both species. That's why for SN2, rate equals rate constant times the OH minus concentration times CH3Br or the CH3CH2Br. CH2CH2Br. So these are the answers given in the books. There are some mistakes. It's good that we can make the corrections as well as we go. And so somehow the rate depends on the both. And we know that it goes through this kind of transition state to give you these stereochemically inverted product. So hence in the presence of hydroxyl, actually this alkyl halide hydrolysis is actually initiated by the hydroxyl because it's much better nucleophile than water, and hydroxyl will attack. So therefore, if you add sodium hydroxide in the presence of, if you add hydroxyl or sodium hydroxide to ethyl chloride or ethyl bromide, so this is the reaction happening. So therefore, the rate law has hydroxyl in it. So the rate depends on the hydroxyl concentration. So therefore, it's very easy to say that if we increase the concentration of sodium hydroxide, so that means you're going to increase the hydroxyl concentration, therefore the rate will increase. So the rate will increase because of this. So you just have to show that this is happening through SN2 mechanism, and the hydroxyl attacks the carbon at the same time bromine is leaving, and the rate law, if you write the rate law, it clearly shows the rate depends on the hydroxyl concentration. So therefore, what you have to say at the end, so hence addition of small amount of sodium hydroxide does not change the rate of the reaction of tertiary butyl chloride, because it's it's a SN1 mechanism. There's no in the rate law, there's no hydroxyl or water involved. Only the tertiary butyl chloride is there, which undergoes the removal of chloride, the leaving group, and creating or giving you the carbocation. But ethyl chloride is a primary alkyl halide which undergoes nucleophilic substitution via SN2. And it's a bimolecular reaction, so that's why it's called 2. And the rate of the reaction depends on the concentrations of both reactants. So that's what we saw. So that is how you approach this question and answer. So it's all, the main difference is depending on whether you have primary, secondary, or tertiary. So alkyl halides, they will undergo different mechanisms, SN1 or SN2. So then depending on SN1 or SN2, there are 2 different mechanisms. The rate law changes, and so does the mechanism. Okay. Okay, the next question. So it's asking, explain why solvolysis or hydrolysis of the following compound A in aqueous ethanol. In aqueous ethanol, that means you have ethanol and water together. Aqueous ethanol undergoes about 600 times faster than comparable reaction of tertiary butyl chloride. So the tertiary butyl chloride is this. Okay. CH3. So this reaction is they say this reaction is much faster. So if you compare the K, so this will be K1 and K2. K1 will be like 600 times faster. It's about, that's what they say. So this reaction is, solvolysis of this compound A is much, much faster than the reaction of tertiary butyl chloride, the same solvolysis. So the reason being, we know that when you have bulky groups, like tertiary butyl group or this compound A, which is really, really, really bulky, and they undergo this solvolysis or this nucleophilic substitution reaction through SN1. And in SN1, the first step is to make the carbocation, as we saw before. And this carbocation formation, during that carbocation formation, see these, if you use this diagram again, see, if you look at this carbocation formed during the SN1 reaction, it is flat. It is flat, and so no three-dimensionality. So like, it's a flat molecule, flat carbocation. And so that's actually is the main reason why these bulky groups, compounds with bulky groups, they prefer SN1 mechanism. So these, the carbon atom, this carbon atom, which is connected to the chlorine, they're all tertiary carbons. This carbon is tertiary, and this one also tertiary. Okay, and so therefore, the first thing you need to mention, therefore, since they are tertiary, they will undergo SN1 mechanism. So that's something we already discussed. So what happens, what they're saying is, if you compare the tertiary butyl group and this compound A, so when you're going from tertiary butyl chloride to compound A, you have increased the steric crowding. So steric crowding has increased. So because this A has bigger groups, much bigger groups. But when you do this when you increase the steric crowding, now what they say is the rate has gone up. Why it is the case? So that is what we're trying to address here. So the reason being, because of these huge or the bulky groups, they have something called steric hindrance or steric bulkiness, which is not that favorable. So then they try to relieve that, they try to release that steric bulkiness or the steric hindrance or the steric compression by removing the leaving group, because that will generate this flat carbocation where you will have less steric hindrance. So the planar carbocation, so that is the driving force to make that planar carbocation. So therefore, in A, steric crowding is much more than the tertiary butyl chloride because of the presence of the two bulky groups. These are two bulky groups. Therefore, steric crowding in A is much bigger than the steric crowding in tertiary butyl chloride. Hence, the solubilisis, hence it's pretty much like you can say the reactivity of A is much higher, or it reacts very fast than the tertiary butyl chloride. So that should be the answer. Like in short, so these tertiary alkyl halides, they are under a lot of steric stress or steric compression or steric hindrance. They try to release that by forming that carbocation. So therefore, higher the steric hindrance, so higher the rate. So they will have, because the carbocation will be more stable. In other words, when you have bigger groups, they can push a lot of electrons onto the carbocation, making it more stable. So that's also making faster that reaction. Okay, so that is the explanation for this question. It's the same thing, so I already explained. Okay. Then more questions from the unit 2. This is session 4, review question number 4 of the session 4. So actually you can go back to your book and find these review questions and practice more review questions. That'll be more useful for your final exam. Okay. Question says when 2s, 3s is 2s, 3s, 3-chloro-2-butanol. So I hope you understand when I read this name of the compound 2s, 3s. So this is the stereochemistry. This tells you the stereo chemistry of these two positions. The second and the third carbon, they have S stereochemistry or S configuration of that's there's the enantiomers or the chiral centers. There are two chiral centers with S stereochemistry, and it's 3-chloro-2-butanol, and so that is the structure here. And so if the name is given, you should be able to draw the structure. Maybe the structure may be given or not. And these, the way they have drawn, this is called Fischer projection. Okay, so we have learned few ways of writing chemical structures: Fischer projection, Newman projection, then Sohor's projection, and so on. Okay, so then you have to be familiar with those different ways that we draw molecules. And so if the name is given, you should be able to draw the molecule first. So it says when 2s, 3s, 3-chloro-2-butanol or the compound D reacted with aqueous sodium hydroxide. So it's reacting with aqueous sodium hydroxide. See, now you have to, when you read the reaction, you should understand what's going on, because you have a leaving group here, alkyl halide. So it could be more or less like a nucleophilic substitution reaction. And then they say it will give you, when this butanol is reacted with sodium hydroxide, optically inactive, 2,3-butane diol is formed. Given the mechanism, Given the mechanism of the reaction, explain the above observation. So you have to give the mechanism and explain. So you have to show how this reaction is taking place and explain what's going on. And and the resultant product, or the product, is actually optically inactive. So let's see what's happening here. So these special projections, it's pretty much, if you draw it using this Soho's model. So this is the structure. It's very, so the purpose of Fisher projection is you don't have to show the three-dimensionality. You just draw the molecule in 2D. So this is 2D representation of the same molecule. And so, but it's actually, this is, the chlorine and hydrogen coming up. This hydrogen and hydroxyl, they're also coming up. And the other two groups are going down. So these two are going down. So that is the meaning of this Fisher projection of this 2D. So then you can draw, you can draw this mode as well. So before we get to the answer, let me remind you about these Fisher projections, how to interpret these Fisher projections, and how do you determine the RNS using Fisher projections. So this, as I said, this is an attempt to draw these molecules in 2D. So if you have this molecule, having four different groups, A, B, C, D, so that when you draw the Fisher projection as this, it simply means the C and D, which are on the horizontal line, they're coming up. So they're coming towards you. This wedge, it means, it's coming towards you. And the dashed wedge this means going away from you. That is, going away from this plane or below this plane, and C and D coming towards you. And they are coming towards you, and they are above this plane. Or you can understand easily as given here. So it's C and D groups, they are like arms coming out to hug you, something like that. So that's the meaning. I mean, that's how this drawn here, that's the meaning. So C and D come to hug you. So horizontal bonds are wedges, point out of the page. So point out of the page. Vertical bonds are dashes, point into the page. So that's what I just explained. So the horizontal ones are pointing out of the page, and AB, the vertical lines, which are, they're going away from you, or they're pointed into the page. So that is the meaning of this Fisher projections, which are in 2D. So then how do you determine the absolute configuration RS on Fisher projections? So as I said, we already covered this part. So it's the same thing as when you draw this molecule using horizontal and vertical lines. It means you have CD as wedges and the AB as dashes, CD coming towards you and AB going away from you. So remember this is very important. And you have to know this in order to handle with Fisher projections. So then we know that to determine the absolute configuration of the chiral center, first you need to find the chiral center. And so that is your chiral center here. Then what you do is you follow the Kern-Ingold Prelog rules and assign priorities. So I'm not going to go through that again. We covered that in detail. We did examples. Go back to your slides and listen to the recordings and learn if you don't remember now. So you're going to need that for the final exams. So you assign priorities. So this is chlorine is number 1, 2, 3, and 4 as shown here. Then what happens, then 1, 2, 3 trace clockwise path. So as you could see, this 1, 2, and 3, it's a clockwise. Okay. So what we do is we assign the priorities and we keep the least priority one away from us. Then we look at the other 3 atoms, and then we see the arrangement, whether it's clockwise or anti-clockwise. If it is clockwise, we label it as R. If it is anti-clockwise, label it as S. But in the Fisher projections, we don't have to hold the least priority group away from us. So what we do is if the least priority group is coming towards you, like as here, this hydrogen is the least priority group, it's coming towards you because it has a wedge. And so it's a dark wedge. So it's coming towards you. Then what you do is the stereochemistry that you determine here, 1, 2, 3, traces a clockwise pattern, then you reverse that. And so therefore, if this, since it is clockwise, it should be, we feel like it is R, but it is not the case. You reverse that to S. Okay, so I'm going to say that again. When you get the priority, when you assign the priority and determine their pattern clockwise or anti-clockwise, if the least priority group, like the hydrogen in here, and if it is coming towards you, then you reverse the stereochemistry that you determine. Okay, so therefore actual stereochemistry of this carbon is S. So that's how you do it. So therefore, so this is summary. You can read the same thing. So you have to remember that if the least priority group is coming towards you, if it has a dark wedge, you reverse the stereochemistry to get the final one. So again, another example. So first you identify the chiral center, it is here. So then you can draw out the side groups as wedges. So you're gonna have to draw this again. And so the horizontal ones as wedges, and we don't have to worry about the vertical ones, we know that. So because we need to find out the least, what happens with the least priority group, then you assign the priority and you determine the stereochemistry. So just to remind you about the priorities, see, like you assign the chlorine as priority number 1, and this the other one, hydrogen, for sure it's priority number 4. But then now we have a tie between these number 2 and number 3, because they all have the first atom as carbon. See, here also carbon, here also carbon. Then you go to the next step. So next step, the next atom. So this carbon is attached to bromine, and this carbon is attached to 3 oxygen atoms. And we know that bromine has higher priority, and therefore this carbon is given number 2, and this carbon is given number 3. So that's something to remind you. When you have a tie, like when you have the same atom on both sides, then you have to go to the next atom and see whether you can distinguish or whether you can assign priorities there. If the second atom also equal, then you go to the third step. So we have discussed all this in detail. So look at the slides, listen to the recordings if you don't remember. Okay, so again, in detail, so after you assigning the priority rules, Carr-Ingold-Prelog rules, see now, traditionally or conventionally, what we do is, according to the Carr-Ingold-Prelog, we place the number 4 priority group in the back. Like we hold it. It's like we say, we hold the least priority group away from you. Then you look at the other 3, like A, B, C. So the least priority group, D, you hold it away from you, then you look at this ABC, right? So then if they are priority changes anti-clockwise, then it will be yes, that's how you do it conventionally. But here in the Fisher projections, if the least priority groups are coming towards you with a dark wedge, so what we do is we don't rotate the molecule. Do not. Instead of rotating the molecule to put number 4 in the back, just trace the path 1, 2, and 3, and then reverse the result. So that's again the same thing that I just explained before. So you're not going to rotate the molecule and try to hold the hydrogen away from you or the least priority group away from you. Just assign the priority first, then trace, draw that curved arrow. And so now in this case, this is 1, 2, 3, it looks like R, but then since least priority group is coming towards you, you reverse that. So therefore the absolute configuration of this carbon is actually S. So that is how we do that. More examples. So we can go through these examples and see how we have determined the SNR, and you can follow the same method that I explained now. Okay, back to the problem. So they're asking about if you don't remember the question again, when 2s3s3-chloro, this molecule reacted with sodium hydroxide, it gives you optically inactive 2,3-butanediol. So you have to give the mechanism. So the reason I explain these Fischer projections, because if only this one is given, you should be able to draw this molecule. So see, we can draw this molecule as, CH3, that's the vertical line, and we know that it's going down or it's going away from you. And let me draw this again. Okay. So actually, vertical lines, they're going away from you, and the horizontal ones are coming towards you. Therefore, this CH3 and this CH3 is actually going down, and this OH coming towards you, this hydrogen coming towards you. And this hydrogen also coming towards you, and chlorine also coming towards you. So that is the three-dimensional structure. So this is 2D and this is 3D. So then again, you can draw the SOHO structure as well. So see, even in the SOHO structure, that'll be easy. Drawing the SOHOs will be easier than using this guy. So this is your SOHOs structure. So if this kind of question is given, so it's better that you draw this one first, so then you have an idea. See, the horizontal ones, always the horizontal ones are they are wedges. The horizontal ones are wedges. They're coming towards you. Vertical ones are going away from you. So the middle bond is on this plane, and the CH3 groups are going into the page or going away from you. So then the SOHO structure, see this chlorine and hydrogen coming up. So that's the meaning. So see, they're going up. And then hydrogen and hydroxyl of these, hydrogen and hydroxyl, that's also coming up. But we know that, so this is, as I said, nucleophilic substitution reaction. And you have nucleophile and also the leaving group in the same molecule, right? So let me erase this for clarity. So see, the hydroxyl group, where's my pen? Yeah, the hydroxyl group, this hydroxyl group, it's a nucleophile, right? Because it has lone pairs, it can attack. And you have chlorine, which is a good leaving group. I mean, not a really good leaving. It's a good leaving group. And hydroxyl is a nucleophile in the same molecule. And then hydroxyl may be able to attack this carbon, which is bearing the chlorine, which is the leaving group, and kick out the chlorine to make an intermediate. I'll talk about that in a bit. So having the nucleophile and also the leaving group the same molecule, I mean that reaction is possible. But with this angle, it won't happen. In this, because we know that in these molecules where you have this sp3 hybridized carbons and you have the single bonds, they can rotate. They can rotate. And when you rotate this, let's say this carbon 1 and carbon 2 bond, so when you rotate, you get conformations. So we learned that, okay? We learn about conformation of ethane and butane, right? Like CH3, CH3. We learn about this, conformation of these ethane. Then also CH3, CH2, CH2, CH3, butane. So make sure that you understand the concept there. But for this attack by the hydroxyl on chlorine bearing carbon won't happen, in this conformation. But when you have this situation, so I hope you remember we learned something called anti-periplanar during elimination reactions. When we learn eliminations reactions, we learn anti-periplanar situation. So this reaction will takes place when hydroxyl and chlorine is anti-periplanar to each other. So therefore, first thing you need to do is you rotate the molecule until you get this anti-periplanar situation. And I mean, the stereochemistry does not change. You rotate both carbons so that hydroxyl and chlorine are anti-periplanar to each other. And once you have rotated that molecule, so which is, now the hydroxyl and chlorine are anti-periplanar to each other, now the hydroxyl can attack this carbon, chlorine leaves. So in that situation, because this is nucleophile and the leaving group in the same molecule, so you end up making this three-membered ring structure, because there's only 1, 2, 3. It's a ring. So that's why we call it the three-membered ring, because now hydroxyl and this carbon is, this carbon is, they're connected. And now, because oxygen donated the 2 electrons to this carbon, by attacking, and then now the chlorine has left, and the oxygen is positive. So when oxygen is positive, so it becomes an electrophile. So, okay. So now this molecule is more reactive towards the sodium hydroxide. Now, remember, they are adding sodium hydroxide as well. That means it gives you OH minus. But this, if you look at this molecule, having chloride, that also, could undergo, let me erase now all the other things to make it clear. So you may wonder why this does not undergo, why this does not undergo this kind of reaction. This is primary alkyl halide, and so therefore, SN2 reaction is possible. But the thing is, electrophilicity, this carbon also electrophilic. Electrophilic means they are looking for electrons. And so this is nucleophile, and they are rich in electrons, so they're looking for positive charges to attack. This electrophilicity of this carbon, and the electrophilicity of these 2 carbons, which one will be higher? So electrophilicity of this these 2 carbons in this oxonium ion. So when you have positive charge on the oxygen, we call it oxonium ion. So therefore, this electrophilicity of these 2 carbons are more high. I mean, they are really high compared to this carbon, compared to this one, compared to their primary alkyl halide. The electrophilicity of these carbons are more higher. And also the intramolecular attack of this hydroxyl to chloride is also it's easy, and it happens at a higher rate. So therefore, this is the first step. So the intramolecular attack happens before hydroxyl attacks this carbon for an SN2 mechanism. So don't worry too much about that details, but just remember this intermolecular reaction is more favorable first, giving you the oxonium ion. Now it is more susceptible for the attack by hydroxyl because to relieve these 3-membered rings are not that stable. They are under a lot of steric hindrance. So to relieve that stress, and also now these carbons are more electrophilic, and so then it will undergo attack by the hydroxyl. But if you look at this molecule, it's a very symmetric molecule. So you have CH3 group here, CH3, and it's very symmetric. Therefore, attack by hydroxyl has equal probability to attack carbon 1 or carbon 3 here. Okay, let's say, just arbitrary numbers. Don't worry about that. This carbon 1 and carbon 3 have same susceptibility or same probability to get attacked by the hydroxyl group. So then if the hydroxyl attacks, let's say A, so this, okay, let me erase again to make it more clear. So too much writing. Okay, so if the hydroxyl attacks A, this will open up, this bond will open up onto hydroxyl to remove that positive charge. Then you will have this hydroxyl attached to this carbon. And so then you will get this molecule, because this is, hydroxyl attacking from underneath. So then you have these two hydroxyls. And so then the Fischer projection will be, you can draw like that. And hydroxyl attacks the B carbon. So then this will open up onto this hydroxyl, and this hydroxyl will be on the top. So that is very important, okay? See, so if the incoming hydroxyl, nucleophilic hydroxyl attacks carbon B, this carbon, and this will open up onto hydroxyl, and see, this will remain on the top. See, this is the top one, right? And since this hydroxyl attack from underneath, and it will be at the bottom, okay? So then you can draw the same in Fischer projection. Like if you see, like this may be a little confusing, but if I show you how to draw this. See, now this molecule, so if you rotate a little bit, if you rotate maybe like 45 degrees, then you have, see, this hydroxyl will come to this place, and this CH3 comes to that place, and this hydrogen is here. See, therefore this CH3 is actually, this CH3 is going down, this also going down, and these hydroxyl and hydrogen, they're actually coming up towards you. So I hope you can understand that arrangement. You have to see that for yourself. Because if you think about that, see this, if you look from this side, see this hydrogen and OH relatively, they're coming up, and the CH3 is in this CH3, the CH3 going down. That's what we have drawn here. So this is how we're going to get the products. But then they're also saying you're getting the optically inactive mixture, and they're meso compounds. That's a racemic mixture, but they're meso as well. Meso means, so these two are chiral centers, because this carbon has 4 different groups, and this carbon also has 4 different groups. Then you have 2 chiral centers, but this molecule overall optically inactive. Why optically inactive? That means no enantiomeric activity, because there's plane of symmetry. Okay, since you have a plane of symmetry in the molecule, we call them as meso compounds. But the other thing is, this is also a meso compound. And other thing is, since this hydroxyl can attack these 2 carbons in equal probability, and therefore you getting, let's say this is product 1, product 2, you getting product 1 and product 2 in equal amounts. So when you have enantiomers in equal amounts, we call it a racemic mixture. So racemic mixture is where you have equal amounts of the 2 enantiomers, equal amounts of 2 enantiomers, then we call it a racemic mixture. Okay, so that's why these 2,3-butane diol, see, 1, 2, 3, 4. So therefore 2,3-butane, now it's a butane, 2,3-butane diol, it's optically inactive. So that is how we explain. So you're going to need the knowledge of the Fischer projections. Then you need to convert that into SOHO structure. Then you rotate so that your internal, intramolecular or within the molecule nucleophile and the electrophile attack, so that you rotate until that you have anti-periplanar arrangement. Then you do the reaction, the first attack of the intramolecular attack of the hydroxyl to chlorine, chlorine-bearing carbon. You make the oxonium ion, then the oxonium ion will undergo attack by the hydroxyl, the added nucleophile, the sodium hydroxide. And since it has equal probability, you'll be getting these two products. And make sure that you first draw the Sohos model, then convert that to the Fisher projection, and then you can argue, they're getting the same, you're getting the same stereochemistry. That's why it is optically inactive. And individually, these molecules are meso. Meso means you have more than one chiral center, but since the molecule is very symmetric, or it has mirror plane, so it has a mirror plane, it's actually 4 a.m. in the morning, so maybe I'm feeling sleepy, so I can't write anymore. So it's a mirror plane. Okay. So that is how you explain this the question and give the answer. So very similar, this unit 2, session 4, question number 5, very similar. I'm not going to explain this in detail. It says giving appropriate mechanism. So in organic chemistry, many of the questions or many of these organic concepts involve mechanisms. So therefore, you don't have to be afraid of mechanisms, but try to learn them, try to digest properly, and then learn how to how to explain reactions using mechanisms. So they say giving appropriate mechanisms, explain the formation of the given products in each of the two reactions. So this is a reactant, and if you add HBr, you get this, and it's a meso. Say it's a meso compound, see, because you have two chiral centers, but then you have plane of symmetry. Again, here you react the same, similar molecule with HBr, and you're getting plus or minus 2,3-dibromobutane, because again, it's a mixture, and you're getting plus or minus means it could be, because this optical activity, optical inactive and optical activity means the ability of these molecules or this mixture to rotate that plane polarized light. When you put plus and minus in the front, that means it's a racemic mixture. It rotates the plane polarized light in the both directions in equal amounts by these two molecules. That's why it is plus and minus. So it's a racemic mixture. Overall, it is actually optically inactive. It's a similar, you can draw a similar mechanism. So when you have, you get the Fisher projection, you draw the Sohos model, and when you have HBr, so it's an acid, right? And also you have alcohol in the molecule. So this gets protonated first. This gets protonated first. Then it becomes a good leaving group. So this protonated by this hydrogen coming from the HBr acid. So then this becomes a better leaving group. Then the bromine attacks this carbon. Again, you make this oxonium ion type. This is not really an oxonium ion, but it's very similar to that, because this could be, you can say this is bromonium ion, bromonium ion. So that's another mistake in the answers given in your book. So this is not oxonium, it's actually bromonium, because here we have bromine. So the bromine also has, lone pairs, and it can attack this carbon because it's bearing a good leaving group. So then you get this three-membered ring, and similar to the oxonium ion that we saw before, the bromide can attack these two carbons, giving you two possibilities. And so that's why so these all are the meso compounds. They are meso compounds, and then these 1 and 2 in the equal amounts. And Therefore, the overall mixture will be optically inactive. And very similarly, the other one also can also be explained the same way. So I'm not going to explain again, but the same answer in a different compound, bromonium ion, not oxonium ion. Okay. Yeah, that's all the questions that I wanted to discuss. I hope you get the idea. And so if you still have questions, you can email me before the exam. And I know you have emailed me a lot. Some people have emailed me questions. So I will get back to them as soon as possible. Okay.